So hello everyone, so welcome to our this week Rigorous Efficient AI seminar. And today we are very honored to have Dr. Shaoshan Liu from the PerceptIn company to give us this talk, Building Computing System for Autonomous Machines. And Dr. Liu is the founder and the CEO of the PerceptIn company and an intelligent robotics company. His technical research focused on autonomous driving technologies and robotics. He has published 100 research papers, 40 US patents, and over 150 international patents. Dr. Liu have published 3 books on robotic technologies, creating autonomous vehicle systems, engineering autonomous vehicles and robotics, and robotic computing on FPGAs. He is a founding member of the Baidu USA, where he built the autonomous driving system team and performed R&D work at LinkedIn, Microsoft Research, INIA, Intel Research, and Broadcom. He's a senior member of the IEEE, a distinguished speaker of the IEEE Computer Society, and a distinguished speaker of the ACM. And he is also a founder of the IEEE Special Technical Community on Autonomous Driving Technologies. He received a Master of the Public Administration from the Harvard Kennedy School and a PhD in Computer Engineering from the UC Irvine. So now let's welcome Dr. Liu give us this talk.
Well, thank you so much for the introduction, and thank you so much for the invitation, Dr. Yuan. I think you have quite a successful seminar. So today I'm going to talk about building computing systems for autonomous machines. I guess this talk will be quite different from your previous talks from other guests, because I came from an entrepreneurial background instead of a pure technical background. So I will start with the business side instead of the technical side. So here's the diagram I compiled. It's called the rise of the autonomous machines, because I believe autonomous machines will be the next big things for the next 2 to 3 decades. There are enormous opportunities in this domain, but from a business point of view, you need 3 things to be successful in business. First of all, I think many of you are either students that are who are interested in autonomous machines or interested in AI in general, or you are researchers in this domain. Some of you may choose to become, for example, a professor to pursue an academic career. Some of you may go to the industry to become a research scientist in a leading industry lab. And some of you may choose the business route like I did. So if you did choose the business route, congratulations. There are a lot of opportunities there, but also be careful. It's not that easy to launch a startup. Here's something I summarize. For anything to be successful in business, you need at least 3 things or 3 layers. The first of all, you need a killer app, a very good application to start with, so that you fulfill a need. Then on top of that, to fulfill that application, you need your proprietary technology. But more importantly, you need a very mature supply chain to sustain your business model. That's what Apple and Tesla did. They started with an unfulfilled need, whether it's a smartphone or a smart vehicle. Then to fulfill that technology, they scout for mature supply chains. Then on top of the supply chain, they build their proprietary technology. Then they became a $1 trillion business as of today. So it's top down. You need to start with the application. Then there are different kinds of startup that you start with a proprietary technology, probably something that you built within your lab. Then you think is of some value to the business side. Then you develop deep into that technology, waiting for someday that people would acquire you, such as the roadblock approach. That's one approach too, but it's a very uneasy road ahead. But there are some success stories in that. For example, deep learning startup Nirvana was acquired by Intel for some amount of money. Nirvana did not have a very deep business case, but it did create a roadblock for Intel in the deep learning space. So that's another success story. So there are different approaches to do startup. In case you want to leverage your AI expertise to launch a startup someday, welcome to talk to me. I like to talk to people who like to launch startups so that you don't have to step through the obstacle like I did. So let's get started on the real meat of this presentation. So pretty much the motivation came from my own business experience, the roadblock that I had to go through when I developed my business. So there are different parts in this talk. First of all, what's the motivation behind autonomous machines? And then what's on machine computing? Today we talk a lot about AI, different kind of algorithms and so on, but the on-machine computing system is key to success. Then like any other mobile systems, robots or autonomous machines, they are mobile systems as well. That's why they need cloud computing support. On top of that, they might work with each other to share information like a MapReduce system would do. So there would be a cooperative autonomous driving approach or cooperative computing approach. Then at the end, I'll present a few interesting case studies. First of all, why autonomous machine? I believe autonomous machine is the biggest opportunity in the next 2 to 3 decades to come. If we look at this market, about 10 years ago, it's fairly small size, probably a few $1 billion. But in the past few years, it's been growing like crazy, 22% CAGR, annual growth rate, 22% annual growth rate. By 2030, it's a $1 trillion market. But then if you look at robots or any kind of autonomous machine today, they are able to do very basic tasks, but nothing interesting. So only the basic chores that they are able to do. The problem, they don't have a very good computing system to power them to do different kinds of interesting tasks. So the solution is to implement a computing system that can handle all basic tasks in hardware so that we, the application developers, can reserve the brain power for more interesting applications. And that's what happened in the cell phone era as well. If any of you are old enough, you ever owned a Nokia feature phone. Back in the days, the feature phone days, it's a fairly small size market as well, $10 billion market. And then any of those feature phones will spend 90% of the compute power on basic functions, such as communication, only 10% on user application. But then there came Apple and the smartphone evolution. With the smartphone today, it's almost a $1 trillion market today. Whereas on each smartphone, whether it's Android or whether it's iPhone, 90% of the end user application, 90% of the compute power are spent on end user applications, such as YouTube, Instagram, Facebook, etc. And then many of the accelerators actually go inside the mobile SoC to accelerate different kind of functions. Only 10% of the compute power is spent on basic functions. I guess we will see a very similar trend for autonomous machine computing. And that's why this field is extremely interesting today. So if we look at a robot's brain, if we look at its power distribution, there are several basic functions in the robot: perception, localization, planning. Those are the basic functions. Then at the end, you have application. If you look at current design, 90% of the compute power is spent on these basic functions, whereas we want the proposed design to be 80% or more of the compute power are reserved for interesting applications. Only 20% will be spent on basic functions, like the diagram on your lower right side: sensing, perception, decision-making, and so on. So that's the challenge we face today. But let's step back. What's an autonomous machine? Let's take autonomous driving, for example. If you see the car on the left, that's the basic technology stack for an autonomous vehicle. You have the sensing part, you have different kind of sensors that you need to deal with. So unlike traditional computing, that are less strict on sensor requirements, for robots and autonomous machines, sensors are very big parts in the computing stack. When you design a system, you need to consider sensing restriction as well. Then once you have sensing, you have the sensor data coming in, then it go into the perception pipeline, including localization, object recognition, object tracking, or the AI function. And then once you understand the environment, you need to make decisions about the next move of the robot. To integrate all these pieces together, you need a very good operating system and the hardware platform. And remember, they are mobile systems, so they need cloud support, and which we will touch upon in later part of this talk. And then for any part of the talk, if I discuss some technology point, if there's a reference, I will put it at the bottom of the page as I show here. So if you ever need a reference to that specific technology, you can always find it at the bottom of the slide. So let's get started on machine computing. I came from entrepreneurial background, so I would always like to start with a real business story. PerceptIn, we were to build autonomous vehicles and ship affordable autonomous vehicles to serve the public. But because of the lack of a mature supply chain, if you can recall in the first page of the slide of this talk, we mentioned you need a killer application, you need a proprietary technology, and then you need a mature supply chain. When we launched the company, there was no mature supply chain. So that's one of the biggest roadblocks we have to step through. So the supply chain that was missing was compute system. When we launched the autonomous driving business, we had three options. First option, which we preferred because it was the most affordable, most economical option, is to optimize the existing commercial mobile SoCs, such as Snapdragon 820. If they were able to sustain autonomous machine workload, then we will have a win because it's cheap, it's backward compatible, and it's forward compatible. So that's option one. Option two is to procure specialized autonomous driving compute systems. But back in 2017, 2018 timeframe, those systems are black boxes, meaning that you don't know what's going on inside. On top of that, they're extremely expensive. So that's against our business model. The third option, which we would not want to choose, is to develop proprietary autonomous driving compute systems. The reason we would not want to go that route because that would burn up a lot of our R&D budget and effort. Also, they would delay our shipment. So the whole business case is summarized in this paper, Critical Business Decision Making for Tech Startups, our retrospective study. If you're interested in the business side, you can check out this paper. What happens is that we did a thorough study on mobile SoC. Conclusion is that mobile SoC, although they have a lot of compute units, but there are memory problems, there are sensing problems. They're not suitable for autonomous machine workloads, and they are not optimized for it. So option one is out. Option two, we did not want to try. We jumped to option three. So option two, we did not want to try, reason being that it's very expensive. It's a black box, especially when you develop autonomous driving workloads. You don't want to use a black box because you cannot tell whose responsibility it is when there's something happens. It's very hard to debug. And then for example, when NVIDIA PX2 just came out, it cost over $10,000 a piece. We cannot afford that. Option three, we had to develop our own proprietary system. We did not want to choose that route, but as a technology startup, but the supply chain was not ready, so we had to go that route. That burned up half of our R&D budget. So if you were ever thinking about launching a startup, think about supply chain first, whether the market has something that's ready for you. Take autonomous driving, for example. There are a lot of constraints. For example, latency, throughput, energy, thermal, cost, safety. You have to satisfy all of these constraints in order to ship the products. We did ship the products. It took us quite some effort. All the efforts were summarized in this micro 2020 paper. It's called Building the Compute System for Autonomous Micromobility Vehicles. In there, we summarize all the design constraints and optimization that we chose. A very short summary, you have all these different kind of workloads, and you have to deal with all these different kind of sensors. First task, how do you synchronize all those sensors? Make sure the data that you get are clean, that can be perceived by the robots. So sensing and computing co-design, I think that's the first innovation that had to go into the system. Second thing is that you have a long pipeline. You do sensing, you do perception and planning. You have to combine all those algorithms into a pipeline that meets all the real-time and reliability constraints. So ended up, we built a system that combined multiple components. The sensing components are attached to FPGA. The reason that we chose the FPGA for two reasons. First reason, it's perfect for sensor synchronization because you can burn the sensor synchronization logic in hardware. Also, FPGAs have very good very good I/O interface, so that you can connect to pretty much any type of sensor you want. Third, they have something called partial reconfiguration. You can change part of the chip at runtime without sacrificing performance. So we use the FPGA for front-end processing to filter down the amount of data by about 10 to 100-fold. Then it goes to the back end, which consists of multiple CPUs and GPUs for further processing, the heavy lifting of deep learning, for example. Using this design, we were able to cut the cost of existing compute system by about 10-fold, and we can control what's inside the system. So we managed to ship product with this design with cost efficiency, energy efficiency, and safety guarantees. Next, we step back. We think if every time we had to ship a product, we need to design a system from scratch, that wouldn't be efficient. And then every time you have a minor tweak to the workload, you have to shift the system, that wouldn't be efficient. Is there something that's so common to robotic workloads? So we study a bunch of robotic workloads. On the left side, it's one extreme, autonomous vehicles. For each module or for each box, it's a module within, and then their connection relationship and their frequency relationship, their real-time constraints, and so on are listed here in the figure. On the right side, it's the simplest form, pretty much the simplest form of a robot, which is the cleaning robot. You see some common patterns within this design. We summarize all the patterns in the paper down below, but basically they form data flow graphs. The data just flow in, you don't need any instruction. The data just flow in, go through the modules and produce results continuously. Also at the beginning, it's like a funnel, a huge amount of data coming in, but at the end, small amount of data coming out, and they form very beautiful data flow graphs. Those are the common traits. So if we were to summarize the traits, first of all, it's continuous input provide abundant parallelism. In traditional von Neumann architecture design, you have a fluctuation in parallelism, but in robotic workloads, you don't quite see that because data just keeps flowing in. And then the second thing is flexible dependencies. In traditional consumer-producer relationship, you have the consumer has to wait for the producer. In robotics, if you drop a frame, it's okay. Nothing you can do. If you drop a frame, you take the latest frame and do the calculation. So the dependency between the consumer node and the producer node are kind of relaxed. Third, data communication are deterministic. In traditional von Neumann architecture workloads, they are not deterministic. That cause a lot of trouble, especially for memory allocation. But in robotic workload, they are quite deterministic. That's something we can leverage on. At the end, no loops. They're DAGs. They form DAGs between the nodes, but no loops. So that's, in a way, stateless, in a way, simplify the design. So why not build a data flow kind of architecture plus domain-specific accelerator for each module? With that design, you can easily program a robot in a few lines of code. In this example, for example, you have only a few modules, perception, localization, planning, control, and then you have a robot, and then they sense the data which is flowing in. So all you need to do is to have a few lines of code to connect the graph, and then to make sure that each module is able to deal with the complexity, or each module is configurable to adapt to the environment. And that's our design. Data flow architecture plus domain-specific accelerators for each module. And that's been our research work in the past 2-3 years to focus on each module. What's the optimized design for each module and so on. So to dig deeper, we have an example in 2021 micro conference is that we took a localization workload and we designed an architecture for it. The architecture is built on a piece of FPGA so that it's reconfigurable. So what happens is that when we form the data flow graph, say there's a node called localization, that the software will specify the requirements for this module. For example, the frame rate, the resolution, the accuracy, and so on. Then the FPGA or the accelerator would take that specification and check whether it can satisfy that specification. If it can satisfy the specification, then the whole system will do buffer allocation to form the data flow graph. And then because it's a piece of FPGA at runtime, it's able to self-optimize itself. For example, if you are a localization module, you are in a very clean environment with not much feature, then you can kind of turn down your resolution to a lower resolution to reduce energy or to save power. So that's the beauty of the design. We kind of separate the individual function into a domain-specific accelerator. And then we use Dataflow techniques to connect these modules to form a very efficient system. So what are we doing currently in the on-machine computing, or what are the opportunities for research in this domain? For example, if you were to create a roadblock company to focus on one domain, what can be done? First, it's language. Although there are systems out there, such as the robot operating system, there is no universal language today to describe the behavior of a robot. Actually, the behavior of a robot can be described with only a few lines of code if you can design a very clean interface. Second thing, what about security? Robots, they are very prone to errors. So security is a huge research opportunity in this domain, especially hardware security for robotic workloads. And then next comes reliability. For a robot, especially high-speed robots, such as a car, reliability is the most important thing. You never want a robot to harm any person or even harm the robot itself. Then last one is always performance. So these are the opportunity for research in this domain. It's quite an empty field today because there's no even a universal architecture for robotic workload yet, let alone language, security, reliability, and performance. So if you are a researcher looking for an exciting direction with huge market potential, I think on-machine computing is the way to go. Then next is cloud computing. Remember, all these things are mobile systems as well. They move, they need to connect to the cloud to offload some of the computing tasks. So that's the first generation of cloud computing for autonomous machines that we built back in 2015-16 timeframe. I think it's still pretty much the only paper discussing cloud platform for autonomous machine or autonomous driving out there. Basically, for autonomous driving, when you have a cloud, what do? You have three major workloads. The first workload is to build high definition maps that are required for different kind of autonomous driving systems. The second workload is you need to do simulation to understand or to simulate the environment for the machine to perform in. The third is model training that you guys are very familiar with the recent development of deep learning. So they were equal workloads back then. So the challenge was to build a unified compute and storage system to serve all three workloads, as if these all three workloads are first-class citizens, they're equal. But something changed in the past 4 or 5 years. Now the workloads are simulation-centric. It's more and more importantly, simulation becomes the core engine in your cloud system. And the 3D mapping or model training system becomes peripheral. In our profiling, we found out that 80% of the workload today in the cloud are simulation workloads. So everything will be built around the simulation because simulation can greatly improve your development efficiency and lead to cost reduction. So it becomes the core engine for any kind of autonomous machine systems. So when you were to build a cloud for this generation of autonomous machine cloud, you need to build, you need to optimize for the simulation workload. So what are the current work we are doing for simulation workload or for cloud computing for autonomous machines in general? The first thing that's missing, it's a benchmark. I think academia currently does not have a very good understanding of the requirements of autonomous machine cloud workload yet, but it's as big as any cloud computing workload, so it has enormous potential. So the first thing we are trying to do today is to organize, summarize a benchmark for academia to study the requirements for autonomous machine cloud. Then with that, we can optimize its performance. And even further, it's to develop a language to describe the behavior in the autonomous machine cloud. It's very interesting. What does the language have to do? Because it's simulation, you have to describe the scenario of the simulation you want to do. For example, if I want to run a test vehicle on the street of Paris in the winter of 2021, that's the scenario you want to describe. And the system needs to compile that description into a simulation environment to test the car. And another very interesting area. And for this kind of compilation, there are some previous work, for example, done by Disney Research to describe a movie scene. It's a similar approach. They have a movie to make, then you use the script to describe the movie, then they can create animation based on that scene. It's very similar, but it's a very elegant approach. The third part, as these machines operate, they do talk to each other to form a network of machines to share information to optimize performance. The thing we have deployed is called cooperative autonomous machines, meaning that you have sensors and compute power on the infrastructure side, for example, on the road side to help autonomous vehicles navigate. The first benefit, each autonomous vehicle would have a lot of blind spots with these roadside deployed units to aid the perception of these autonomous vehicles. They can be safer and more efficient. We have summarized the findings for our deployments in the report in DAC 2021. If you are interested, welcome to check it out to describe the challenges and approaches in intelligent cooperative driving approach. So what happens when you merge two autonomous machines? For example, we call the roadside deployment SOR, or system on road. We call the vehicle side deployment SOV, or system on vehicle. They do communicate. The way they communicate is that the roadside will broadcast the perception results to the vehicle side. The vehicle then would fuse the perception result from the roadside and its self-perception into a comprehensive perception of the surrounding environments. Also, they will send data to an very intelligent cloud computing unit, such that there is a central intelligent traffic cloud that can consolidate all information from the edge side, from the vehicle or from the roadside, to form a comprehensive, more or less a God's eye view of the traffic environment, so that they can guarantee that you have the most efficient route planned for each vehicle. They have they also can guarantee absolute safety because they get a real-time consolidated comprehensive view of the environment. So here's the anatomy or architecture of the deployment, such that you have the roadside SOV, then the SOV would talk to the SOR. The SOR would then consolidate the information in the IPC or industrial PC or edge computing unit deployed on the roadside. Then they will consolidate data to the regional server. Then eventually everything will be consolidated to the ITCS, Intelligent Transportation Cloud Computing Unit. So if you look at this figure, you say, gosh, it's very similar to a map-reduced system that Google used or Google invented 10, 15 years back, except that the map-reduced system would process text-based data at its bottom, whereas a cooperative driving system would process multimedia data or sensing perception data at the bottom. But layer by layer, it's doing a map-reduced action to reduce the essence of the information to the ITCS so that we get a comprehensive view of the surrounding. And that's quite an interesting research area to go into as well, because now you are doing the map reduce for robots. I'm sure this will be the standard architecture in the next few years as the more and more intelligent robots or autonomous machines get deployed. But what's the problem in this approach? When you talk about cooperative autonomous driving, the key problem is communication or connectivity still suffer a lot in real-world deployments. Although 5G has a lot of promises, but in real-world deployments, they fluctuate a lot. So how do we deal with fluctuation? We need to have two techniques. One is to compress the data such that we need to use advanced compress techniques for raw data such as LiDAR, because we need the LiDAR data to be sent to the cloud for further processing to generate HD map and so on. Also, we need to, for latency variation workloads, we need to have a fusion engine. For example, if you are a vehicle on road, you're waiting for the data from the roadside, but because of a glitch of your network, the piece of data never arrives. What do? It's the fusion engines designed to take care of that. So another very niche, but very interesting research opportunity. How do you do the fusion engine on the vehicle side, and how do you do the compression engine on the road side? So current work in this domain, we are building a distributed robotic computing framework, or let's put it simply another way, a map-reduced system for robots. Now we have gone through 3 different areas. First is on-machine computing for each robot. Second, it's cloud computing for each robot, for a bunch of robots. Third, it's a cooperation framework for different kind of robots. For each of them, you have enormous opportunity for research and for potential startup opportunities. And now I want to share some case studies. We've been talking about a lot of hardware techniques, but what about software, right? When we build a piece of hardware, we should not forget there are a lot of room for improvement in the software domain. So here is a piece of work that I participated in. It's called CocoPie, such that we can compress a engine or compress a deep learning model, and then through compilation to dispatch this model onto different kind of devices. Turns out the result is quite well. It actually outperformed a lot of hardware accelerators. That tells me when you're looking at optimizing a piece of hardware, software actually still have a very long way to go if you look carefully enough. One example is the application of this technique on 3D detection or object detection in autonomous vehicles. For each autonomous vehicle, they need to spend a lot of compute power to extract meaningful information from LiDAR data, such that you can extract 3D information. But does it have to do on a very heavy weighted hardware accelerator? Nope. You can actually do it on a cell phone, such as Snapdragon, if you can use, for example, CocoPie's compression techniques, such that you compress down the whole point pillar of 3D perception network. You can actually achieve real-time performance on a cell phone. Another example, what about the full level 4 autonomous driving workload on a autonomous system? Yes, it's possible if you can use compression, compilation, plus scheduling. For example, in this low-end NVIDIA chip, they actually have a accelerator called DLA, but not many people successfully utilize DLA. But if we could compress the model and dispatch the model to the DLA and have multiple models running together to achieve a very high utilization score, then we can have a full L4 autonomous driving workload running on a few $100 chip, such as the NVIDIA low-end chip, Xavier. So that's another proof that software optimization also has a very long way to go. So that's pretty much the end of my talk. So I have talked about several things. I've talked about on-machine computing, the real challenges that we have observed in the real world. We have talked about cloud computing, what are things needed, what are the 2 generations of cloud computing architecture for real world workloads. We have talked about distributed computing for robots. How can we build a robotic MapReduce, for example? And then at the end, we have shared a few case studies on software techniques to prove the point that software optimization has a long way to go. Eventually, you can combine a lot of software and hardware optimization techniques to achieve what you want. But for each of these points, it's a very interesting research area and very interesting commercialization area. That's what I have to share for today. Now, it's a good time to break. And if you have any questions, it's a very good time to communicate. And thank you so much.
Thank you, Shaoshan. It's a very informative talk. I actually learned a lot. And any questions from the audience? You can unmute your...
Yes, I have some question. Yes. So first, thank you very much for the very informative talk. Yeah, I learned a lot from there. So I guess summary side, I mean, you give you're basically talking about three pieces. So I know possibly on machine the computing maybe it's I don't know what's your opinion on this? Which one is for instance already have more people working on that, or which one based on your experience? Looks like maybe on machine computing it's the one people right now they are focused on that, but the other two maybe not much. Is that the case?
Yes, that's exactly the case. We see a lot of deep learning accelerator designs in the on-machine computing, but besides deep learning acceleration, actually not much. There are a lot of workloads or on-machine computing workloads that are not deep learning based. People are not really paying too much attention. And the memory allocation, for example, people are not optimized for the whole system, but rather individual deep learning networks in the past few years. So enormous opportunities in on-machine computing. But even that, distributed computing for robots and cloud computing for robots or for autonomous machine have been completely ignored for two reasons. First of all, there's a disconnect between the industry and academia. So academia pretty much does not know what's going on in the commercial side.
Right.
Second of all, there are not too much knowledge in those domains. How, for example, how do you do a robotic map reduce? What's the unique requirement on that has not been thoroughly studied. But I do think either of these three or each of these three would have enormous research opportunities to be grabbed.
Yeah, I guess another thing maybe autonomous machine cloud computing and distributed computing, I guess they require more resources. I mean, for instance, hardware support. I mean, yeah, that's another reason maybe I guess academia cannot, invest too much, I guess. Yeah.
But quite interestingly, Amazon or AWS to be specific is spending huge amount of resources to try to enter the domain of autonomous machine cloud computing. But I guess, again, there's a disconnect. Although they spend a lot of resources, I think at this point, they don't quite understand what's unique about this workload yet. But they see the business trend going to autonomous machine cloud computing.
Okay, yeah, thank you. Yeah.
Other questions from the audience? You are free to unmute yourself.
No more question, maybe I can ask.
Yeah. Compian, you can go ahead.
Can we go back to this autonomous machine learning computing slides? I kind of a little bit forget, but yeah, it would be good if we could.
So you have to say stop. I don't know which one you're talking about, okay. But just let me know.
I just trying to. Okay, machine computing.
This one?
Yeah, maybe we can. Okay, yeah, maybe we can stop here. Yeah, the previous one. Yeah.
This one?
Yeah. Okay, so basically, the reason why this autonomous machine computing system is needed is because, for instance, the autonomous driving cars, we need to, share the information. Yeah. Oh. Yeah, I try to understand why, yeah, I guess because I never touched this field, I try to understand why this one is so important, autonomous machine computing systems.
I see.
Can you
I think
yeah.
Yep, I think that's a very good question. I think it's all economy. So what's the most demand? For example, personal computing back in the Intel old days, the x86 days. Why Intel? because there was a huge demand for personal computing, probably created by Microsoft's Windows system, such that people demand that kind of product. So we kind of optimize the workload for whatever people use on Windows. For example, the spec benchmark, right? We optimize whatever people use on Windows. Then that's the PC era. Then once the PC era has passed, the next big thing becomes cloud computing. I don't remember which one comes first, cloud computing or mobile computing, but let's say cloud computing, for example. Then the golden workload for cloud computing benchmark, it's pretty much MapReduce or Spark. Then people use those workloads to optimize their system because there's huge demand for those kind of workloads. Then next comes mobile computing, then becomes the application, different kinds of apps. Then we see the mobile computing architecture are pretty much SoC that integrate many kind of DSP or small accelerators. But again, it's one workload at a time at the front end. So that's mobile computing. The reason that I brought up autonomous machine computing as the next big thing, because I see the demand. If you look at the market projection, by 2030, it's a $1 trillion market, and we see it growing extremely fast. But people are still using, for example, mobile computing chips or personal computing chips for autonomous machine computing. Can it work? Yes, it can work. Is it optimized? No, it's not optimized because we have not yet do a deep dive into the autonomous machine workloads and to identify the common traits between, for example, a autonomous car versus a robot cleaner. What are the common traits? What can be designed or developed on the architecture side to satisfy the common traits to optimize for performance and power consumption? My personal bet is that autonomous machine computing will be the next big thing right after what I call PC, personal computing, CC, cloud computing, and MC, mobile computing. But let's see, in the next few years, we will see the trend very clear.
Thank you. Yeah. So another thing, like I noticed, like you put like autonomous car and then like robots. Looks like they are like workload are pretty similar, but like the robots maybe like for instance have less requirement, yeah, something like that. Yeah, it looks like they are kind of very similar. Yeah, so
the
I mean, I
pipeline
heard like one.
Yep, go ahead.
Okay, go ahead. Yeah, sorry.
Oh no, I said the pipeline would be or the architecture would be very similar. You are exactly right. What's different is, first of all, the requirement. For example, a robot would not travel as fast, so the frequency requirement or real-time requirement which would be much lower. Second requirement or second difference is the depth of the pipeline. The more complex your robot is, the deeper your pipeline would be. So the harder to manage real-time constraints. But the simpler the robot is, the shallower your pipeline would be, and the easier to manage the real-time constraints, power consumption, and so on. But architecture, they look very similar.
Right. And then like yeah, when I used to talk with people, I mean, I don't know what's your opinion on this. It's like they said, okay, like autonomous driving now, I mean, feels like, although I know like you just said there are still enormous like opportunities, but feels like he said, oh, maybe we should work on like robots instead. I mean, because that's actually, I guess, like more opportunities. I don't know, how do you feel these two fields? Yeah.
Yep, I work in both fields. I started with robotics and more on autonomous machines or autonomous driving, autonomous vehicles later on. My feeling is this: it's quite a business feeling instead of a technical feeling. It's that because cars now have a very high demand, and cars are premium compared to robots in terms of price. So cars would foster a very mature supply chain. Because people want to build cars, they need to build a supply chain to sustain autonomous vehicles. Then once that supply chain is mature, it will trickle down to different kind of robots. So cars would be the first thing, or the first big market, or first wave of the market would be cars. That's why you see Tesla, you see a lot of EV company popping up. But on the other hand, you see Tesla start building robots themselves as well, because now that the supply chain is ready, now that the technology is ready, you can use part of the technology just for robots. So you will see the trickle down business model. That's why I think autonomous machine computing is such an exciting field, because you will serve one sector first, and that sector alone is huge. It's transportation. But then once you expand on that, you can have service robots, you can have cleaning robots, you can have different kind of robots. You can even have robots that can be sent to Mars, for example. It's the same supply chain, pretty much the same compute technology that can be trickled down. That's why I think AMC, or autonomous machine computing, is much bigger than PC, CC, and MC combined.
Yeah, that's a very good point of view. Yeah, thanks.
No problem.
Hi, Tommy. Actually, I have several questions, and the first one, so from the perspective of the computing platform, so you mentioned that so FPGA is a kind of good solution, and you also in your case study section you mentioned that so we can use the Cocoa Pi that targeting mainly on the GPU to do that. So do you think that so the underlying computing paradigm for this the autonomous system is kind of the more heterogeneous one?
Yeah, to be frank, I think there are two competing approaches today. First approach is heterogeneous, just like what I put here. It's a data flow, but then for each module or for the key modules, you need domain-specific accelerators. The data flow is to connect the domain-specific accelerators. That's one approach if you use a modular approach to look at the problem. And more recently, it's Tesla approach gave me a epiphany, such that they use a transformer to combine multiple CNNs into a comprehensive view or representation of the environment. So it's transformer centric. Most of the compute will go into the transformer, and then at the end it will become a huge end-to-end deep learning model. But even though I say there are two approaches, but if you zoom out a little bit, you look at the transformer approach, it's a data flow. Let's face it, it's a data flow as well. It's just that the detailed computation is done by a different approach. So I can argue that it's both approach, they are data flow, but then it's the matter of what kind of domain specific accelerator you have for each unit.
So my follow-up question is that so transformer that is targeted for the deep learning based computing task, right? And as you mentioned that, so in the entire computing flow, so actually there are several non-deep learning based tasks, right? So in that case, so how about, so based on your observation, how about their computational cost among the overall computational burden?
Yep. For example, planning and control in today's autonomous vehicles, they're not deep learning based. But then there are people start using approach to use deep learning to reduce the search space and then apply a traditional approach. So there's a hybrid. I don't think we'll go to the extreme that it's a full end-to-end model. I think it will still take a few years if we ever get there. But then we kind of start seeing the synergy between a hybrid model, even for the non-deep learning based component. We still see some hybrid models.
So do you believe that kind of the entire end-to-end is kind of the future trend, like we can modify the motion planning and the SLAM, all of them to kind of neural based? Or it's kind of too risky because the current technique and motion planning
for the next 5 to 10 years, I think it's too risky, especially for car business. We care about functional safety and so on. But how do you apply functional safety on a deep learning model? That's still a mystery. I think the design automation community probably would have something to say about that. But then car is a very traditional business, so they care, I would argue, too much about functional safety in a way. to tolerate a full end-to-end model? How do you explain that if something happens and so on? So we'll see. But my personal bet, if I were to launch a company today to say I would build a autonomous machine computing architecture, I will still use the modular approach. I think that the architecture will sustain the next decade.
And so go back to my first question. So regarding this, the modular-based approach, do you think that we will, the current mobile SoC, something like that, like an autonomous SoC will be a kind of the future?
Yep.
And like what the Qualcomm right now, they try to promote their solution.
I think it's a very good question. If you think deeply, what's the difference, right? If it's a mobile SoC and AMC, for example, autonomous machine computing. If you use your mobile phone, you pretty much run one front end app at a time. So you optimize for one application at a time. That application might use the GPU or the DSP. So some components are active just for that application, because that's the foreground application that you will optimize for. But then if you think about a robot, all components have to be optimized at all times. If there's one module that's the bottleneck, the whole thing would get stuck. You cannot optimize one at a time. So that it's a very subtle difference, but changes a lot of architecture design. For example, not much data flow in a mobile computing setting. If you swap the app, then something changes. But then for a machine, it's you turn it on, then it just continues to run like that. You don't have to interrupt it, then it produces result. It only reacts to the environment. So that means that you have to optimize all modules at all time.
Thank you. Thank you very much.
No problem.
Any questions on the audience?
Hi, Shaoshan. Yeah, thanks for a great talk. Thanks for a great talk. It's pretty informative. So I remember in one of your slides, you mentioned the challenge of the autonomous vehicles is security and reliability. So I was wondering, can you elaborate more on on which type of the security or which type of the reliability you're talking about?
Well, yeah. First on security, security is quite fun. A lot of people try to hack into an autonomous machine system. There are many different ways. You can hack the sensor. You can jam the operating system. So you can attack from many different layers. Unlike traditional, for example, if you're a PC, pretty much you just hack into the system or hack into the operating system, that's it. Or Stack Overflow, whatever kind of techniques. But then now it's a cyber physical system. There are too many attack surfaces that are exposed. You can hack the LiDAR. I can argue that if you use sensor fusion, it's safer compared to a pure modular approach, because if the LiDAR fails, you can still have a camera and so on. So it just pretty much exponentially increased the complexity of security design. I think that's a very active topic in the security community. If you go through the paper from NDSS, CCS, and so on, you see a lot of paper on that. Quite fun. Or even the industry conference like Black Hat, right? People try different crazy approach to hack the car. And then about reliability, I think that's one of my passion. It's that if you look at just this graph, you see kind of the mathematical model of the real-time computing relationship between different modules. And for reliability, first thing, you need to meet the real-time requirement. And then if you just look at the left side, the very left side of the figure, you see a bunch of sensors. So what are sensors, right? Sensors are the anatomy of the robot, what kind of sensors are installed where. But because of the anatomy, you fixate the detection distance and safety requirements, layer protection, and so on. Then the real-time models are physiology of the system. We don't even have a mathematical model to describe the physiology of the autonomous machine. And we don't have a model or mathematical model, a commonly accepted mathematical model to describe the anatomy of the autonomous machine, let alone you need to connect the anatomy and physiology, at least theoretically, to deduce how reliable your system is. I think that's one domain that we should go into. It's rather theoretical, but it carries a long way because all later models would follow that approach. But we are not seeing any paper on that.
Yeah, I see. Yeah, thanks. Yeah, very helpful.
No problem.
Hey, Shaoshan, I have one more question. So since you are landing on this page, I know you guys use like, for instance, all the Wear iOS. So, but it's like the industry actually use such like, for instance, platform or like systems, like all the Wear or like iOS.
Yep, good question. Not to criticize, but ROS was spin-off from an academic project. It's very good for R&D purpose. For example, in our case, we use ROS for R&D to develop the algorithm because the infrastructure is so good. But then when we launch the product, especially on cars, we use dedicated middleware, for example, QNX, to connect the modules to make sure that it's functionally safe and it meets all the real-time requirements. It does not crash because of out-of-memory errors and so on. So I think in the middleware space, to guarantee reliability and real-time performance, we still need a lot of leap forward to get there. But ROS, I think it's more for R&D or research platform.
Okay, you mean like actually like industry not use that a lot for real production?
Yeah, I cannot represent everybody, but the companies that I know, most of the companies that I know either develop in-house middleware system or leverage third-party suppliers such as QNX and some others, VxWorks and so on.
Okay, so can you explain like I guess like I talk with people on iOS. I mean, people like complain about their like responsiveness and such kind of. I mean, a lot of things like. So do you think like there is an opportunity, for instance, for a new, I mean, kind of OS or middleware for like for these autonomous machine systems?
Yeah, if I were to,
because iOS is not good. I think iOS is actually not developed by computer science people, yeah, but actually they are working on other fields, and I think it's like based on my understanding, it's like in a machine. What's that? Yeah, other department, not like CS people, I guess.
they would argue otherwise, but that's fine. I think they're not developed by systems people, to be exact, but they come from computer science department. But to answer your question, if I were to say launch a startup today, I would definitely go into building an operating system for robots. I would start something simple, for example, simpler form robots. Because a operating system, if you think about it, for one thing, it's reliability and performance and so on. But more important thing is to consolidate the existing supply chains. I think ROS is getting too big, too complex, that they have many different functions and many different sensors. But if you zoom in to the consumer demand, maybe you only have to zoom into 10 sensors, 5-6 modules that can satisfy 80% of the needs. If I can build a system just focus just on that, say 10-20 modules, 10-20 sensors, but 10 times more efficient than ROS, you have a very strong business case.
Right. Okay. Yeah, thanks for this.
No problem.
Any other questions from the audience? We have very hot discussion. Okay, so if no more questions, so let's thank our speaker, Dr. Liu, again. So this is a really very informative talk, and I believe so everyone in talk we learned a lot from the perspective of the industry and what is the requirement and the demand of the future autonomous computing system. So Shaoshan, thank you again. Thank you very much.
Thank you all so much.
Yeah.
Very nice
Thank
to meet you guys.
Yeah.
Thank you.
Very nice to meet all of you. So let's meet next week. Thank you. Have a wonderful
Okay.
day. Bye.
Thank you. Yeah.